Hello everyone, welcome back to the Atharva Academy. Myself Chinmay Daduk. Now in this video we are going to start chapter 8, that is column and strut. So first of all we will understand that what is column and what is strut. So here column is a vertical member which is subjected to axial compressive load. Means any member which is vertical, it may be like this, and it is subjected to axial compressive load. Means if we fix this surface and we apply load in this direction, let's say it is having value P, then it is compressive load acting on the vertical member. So in this case this member is called as column. Clear? And now what is strut? It is a member subjected to axial compressive load and it can be inclined or horizontal or vertical member. Means if we have this type of member and if we fix this surface and we apply compressive load in this direction, then in this case this member is called as strut. And this member can be also inclined like this. Fine. So I hope that you understand basic difference between column and strut. And now by understanding the difference between this column and strut, we can say that all the columns are struts but all the struts are not column. Because here we know that strut may be inclined horizontal or vertical member, but column is a vertical member. Fine. Now understand that for the column and strut same theory is applicable, right? Because in both the cases member is under axial compressive load. Now you have to understand difference between beam and column. Actually some students have wrong idea in that mind that beam is a horizontal member and column is a vertical member, but it is not so. Here I am going to tell you basic difference between beam and column. Let's say we have two members like this. Now in both the member, this axis is going to be the axis along length of this member. So that axis is called as longitudinal axis. Fine. Now if we apply load in this member in the transverse direction like this, means if we apply load in the member in the perpendicular direction to the longitudinal axis, then this member is called as beam. And if we apply compressive load like this, means if we apply load parallel to the longitudinal axis, then this member is called as column. So in the beam we have transverse loading condition and in the column we have axial compressive loading condition. Fine. And actually this column is vertical member, so actually this member should be vertical like this. So if this is vertical like this, then we will say that it is column, and we can say that this member is strut because it is horizontal. Fine. Now we are going to understand buckling. So what is buckling? If member under compression load deflects laterally or it fails due to bending rather than compression, then it is called as buckling of member. So let's say we have one vertical member like this, and here we fix the bottom surface of this body, and on the upper surface we apply compressive load P. So here this member is under compression load. Now generally we know that for compression load sigma is equal to P divided by cross section area, and this is the value of compressive stress, and here we take this value of P as negative because it is compressive in nature. Fine. Here if this compressive stress is higher than permissible stress, then we can say that its material is going to be fail. But let's say if this material do not fail by compression load, but if this column is very long And if you apply compression load P like this, then this member is going to be deflect like this. Means actually it deflects laterally. Means it deflects in lateral direction. Fine? And if it is deflecting like this, then we can say that there is bending in the body, and if there is bending in the body, then this member is going to be fail by bending stress rather than compression stress. And if this column is going to be fail by this type of bending, then we can say that it fails by buckling in the member, and that phenomena is called as buckling of member. Means if this member deflects laterally and it fails by bending rather than compression, then it is called as buckling of member. And here value of load P at which it fails is called as buckling load. Fine? Now we are going to understand slenderness ratio, that is denoted by S. So what is slenderness ratio? It is the ratio of effective length of the column and the least radius of gyration of its cross section. So we can say that slenderness ratio S is equal to effective length, that is denoted by LE, divided by K minimum, that is least radius of gyration of its cross section. So you have to remember this formula. And how to find K minimum? Here K minimum is equal to I minimum divided by A under root. So you also have to remember this formula. And here this equation comes from equation I is equal to A into K square. So from here, if we want to find out K minimum, then we have to take I minimum. In these formulas, this I minimum is minimum value of moment of inertia. This LE is effective length that we are going to discuss later on. And this A is cross section area of column. And this K is radius of gyration. Fine? Now we will discuss type of column. So there are three types of column: short column, medium column and long column. So what are the difference between these three columns? If length of the column is very much higher than other dimension of this column, then we can say that this column is long column. If length of this column is less, then we can say that this column is short column. But how to identify that whether the column is short column, long column or medium column? So to identify column, we use slenderness ratio. So if we find slenderness ratio of column and if it is less than 30, then we can say that column is short column. If slenderness ratio is greater than 120, then we can say that column is long column. And if it is between 30 and 120, then we can say that column is medium column. Fine? Now, if column is short, means if it is like this and we apply compressive load like this, then this column is going to be fail by crushing. Means this column is going to be fail by compressive stress sigma C. If column is long, means if it is like this and we apply compressive load P like this, then this column is going to be fail by buckling. Means it will fail like this. First of all, it will deflect like this and then it will fracture from here. Fine? So long column fails due to buckling. And if column is medium column, means if slenderness ratio is between 30 and 120, then it may fail due to crushing or it may fail due to buckling. So in the case of medium column, we clearly cannot say that it is going to be failed by crushing or buckling. But if column is short column, then we can clearly say that it is going to be failed by crushing load. And if column is long column, then we can say that it is going to be felt by buckling load. Fine. Generally in the question, long column will be given to us and we have to find value of buckling load in the long column. Means we have to find out load at which this column is going to be fractured by buckling. Fine. So now we are going to understand that how to find buckling load. To find out buckling load, Euler's formula is used and it can be also said as Euler's formula. Fine. So here this Euler's formula is used to find buckling load in the long column. And here it is the equation to find out buckling load in the long column. This buckling load PE is equal to pi square EI minimum divided by LE square. Here this E is the value of Young modulus, I minimum is minimum value of moment of inertia, and this LE is effective length of column. After a while we will discuss effective length. Right now understand that length fixity coefficient alpha is equal to LE by L. Means it is the ratio of effective length divided by original length. And this end fixity coefficient, that is denoted by N, is 1 upon alpha square. So you also have to remember these two formula. Most of the time GATE is going to be asked question from this formula. So this formula is very important from this chapter. So you have to know this formula. Fine. Now we are going to understand that what is effective length of column. So if let's say this is the column like this, and if this column is hinged at both this end, then in that case value of effective length is taken as L. Means here if this length is L, then we have to take effective length LE is equal to L. Now I hope that you understand what is the meaning of hinged end. Means here it is having hinge support like this. Fine. Here this type of column is called as column which is hinged at both the end, that is shown here. And in this case if we apply compressive load like this, then there will be buckling of this column and this column will deflect like this. Fine. So here we can show that this column is going to be deflected like this. Now if this column is hinged at this point and if this point is fixed, then this is the case of column which is fixed at one end and hinged at other end. So in this case we have to take effective length is equal to L by root 2. And if we apply compressive load at this end, then this column is going to be deflected like this. Means here it is not going to be deflected directly from here. Fine. Now let's say if this column is fixed at both the end, means here we fix this end and this end, then in this case value of effective length is equal to L by 2. And in this case if we apply compressive load, then this column is going to be deflected like this. So in this case this deflection will be less as compared to this case. Fine. And let's say in the fourth case we only fix this column from one end and this another end is free. Here this end is free. Fine. So in this case if we apply compressive load like this, then this column is going to be deflected like this. Fine. And this compressive load may be here. So in this case there will be maximum value of deflection, and in this case this effective length is taken as 2L. So we have formula of buckling load, that is pi square EI minimum divided by LE square. Now in the question if buckling load is asked, then value of E is given to you and value of I you can find out from the geometry and length will be given to you. So you have to find out effective length from this table. If the column is given as hinged at both the ends, then you have to take this given length as effective length. If it is given that column is hinged at one end and fixed at another end, then you have to take this L by root 2 as effective length. If it is given that column is fixed at both the ends, then you have to take effective length is equal to L by 2. And if it is given that column is fixed at one end and it is free at another end, then you have to take effective length is equal to 2L. And then you have to put this value here. Then finally you will get value of buckling load from this equation. Fine? You can remember these cases in order. In first case it is hinged at both the end. In second case we fixed one end, and in third case we fixed another end. And in this fourth case we remove this fixed end from this end. So it is free at this end. And you can remember this order of length. Now we know that this length fixity coefficient alpha is equal to LE by L. So if you will divide this value of effective length by L, then you will get length fixity coefficient alpha. So here if you will divide this L by L, then you will get 1. If you will divide this L by root 2 by L, then you will get 1 by root 2. If you will divide this L by 2 by L, then you will get this 1 by 2. And similarly here you will get 2. Fine? And we also know that equation of end fixity coefficient is equal to 1 upon alpha square. So once you have value of alpha, you can find out value of n. So that is given here. Fine? Now we know the equation of Euler's formula, that is buckling load is equal to pi square E I minimum divided by LE square. Fine? Now we also know another equations, that is radius of gyration minimum value is equal to root I minimum by A. And we also know that slenderness ratio is equal to effective length divided by K minimum. Fine? So now let's say if you want to find buckling stress, then how can we find out? We know that stress is equal to load divided by area, right? So we can find buckling stress, that is, let's say denoted by sigma B, which is equal to PE divided by A. Means buckling stress is equal to buckling load divided by area. And this is the cross section area of column. So what will be the value of this buckling stress? It will be this value divided by area. So here we can write that it is pi square E I minimum divided by LE square into area. Fine? Now here we have this equation, and in this equation if you will take square both the side, then it will be K square minimum is equal to I minimum divided by area. And here in this equation there is also I minimum divided by area. So we can replace this term by K square minimum. So it is pi square E K square minimum divided by LE square. Fine? And we have also another equation of slenderness ratio, that is LE by K minimum. And here if you will take square both the side, then it will be LE square divided by K square minimum. So from here we can write that 1 upon S square is equal to K square minimum divided by LE square. And here we have this K square minimum divided by LE square, that can be written as 1 upon S square. Fine? So it will be equal to pi square E divided by S square. And that is also equation of buckling stress. So these all are the formulas of buckling stress in the column. Fine? Actually you don't have to remember all these formulas. You can only remember this formula, and you already know these two formulas. So by using these three formulas you can find out all these formulas. Fine? And here to find out buckling stress, you have to divide this buckling load by area. So you will be able to find buckling stress in the column. Clear? Now here we have derived this equation in which this is the buckling stress and this is the slenderness ratio. For any material, value of pi square into E is constant. So from here we can write that sigma B is proportional to 1 upon S square. Fine? So now if you will take any graph in which on this axis if you will take slenderness ratio and on this axis if you will take buckling stress, then you will get one graph and it will be something like this. Here you can see that if value of slenderness ratio is increasing, then value of buckling stress is decreasing. And we know that for short column, value of slenderness ratio is less than 30. So value of buckling stress for short column is very high, right? Because here this slenderness ratio is less, so buckling stress is high. So for short column we can say that buckling stress is high. Means we can also say that buckling load is high. And similarly for long column we know that slenderness ratio is greater than 120. Means if this slenderness ratio is higher, then we know that buckling stress is low. Means in this case buckling load is less, right? So from here we can say that if column is long column, then in that case value of buckling load is less. Means if you will apply low amount of load, then also this long column is going to be failed by buckling. You can understand from this figure. If you apply load like this, and let's say if value of this load is 100 Newton here. So if this column is long column, then this column may fail at lower value of load that may be 100 Newton. But let's say if this column is short column, means it is like this, then to buckle this short column we require higher amount of load. So it may require, let's say, 1000 Newton of load. Means in this case to buckle this short column we require higher amount of load. So for short column value of buckling load is higher. Value of load required to buckle this column is less. So we can say that for long column value of buckling load is less. Fine. Now we are going to discuss Rankine's formula. We have discussed the Euler's formula, that is for the long column. Now this Rankine's formula is used for medium column. So as per this Rankine's formula, 1 upon PR is equal to 1 upon PE plus 1 upon PC. Here this PR is load at which medium column fails. This PE is value of buckling load and this PC is crushing load for column. We know that how to find buckling load. We have equation to find out buckling load, that is pi square EI minimum divided by LE square. And we also know that how to find crushing load in the column, that is equal to crushing stress into cross section area. Fine. So we can find out value of PR by this equation. And this value of PR is the load at which medium column fails. Fine. Now we know that in long column value of buckling load is very less, right? So we can say that buckling load is very less than crushing load. So here this term will be negligible as compared to this term. So for long column we can write that 1 upon PR is equal to 1 upon PE. So for long column this Rankine's load will be equal to buckling load. Means here this Rankine's formula also says that value of load at which long column fails is equal to PE, that is buckling load in the column. Means this Rankine's formula says that long column is going to be failed by buckling load PE. Fine. Now we also know that for short column, value of buckling load is very high. Means it is greater than PC, that is crushing load. So in this case, value of this term will be negligible as compared to this term. So we can write that for short column, 1 upon PR is equal to 1 upon PC. So we can also write that PR is equal to PC. Means here this Rankine formula says that for short column, value of load at which column fails is equal to crushing load. Means this short column fails due to crushing. Fine. For the medium column, we are going to use this formula because for the medium column, these both load are nearly same. So now we have these three formulas. This is the Rankine's formula and this is the Euler's formula. And here this crushing load is equal to crushing stress into area. Means here this stress is the value of stress at which column is going to be crushed. From this equation we can write that PR is equal to PE into PC divided by PE plus PC. Fine. And let's say here we divide this both the numerator and denominator by PE. Then it will be PC divided by, it will be 1 plus PC divided by PE, right? And now in this expression we know value of PC and PE. So now we are going to put these values here. So PR is equal to sigma C into A divided by 1 plus sigma C into A divided by pi square EI minimum divided by LE square. Fine. And now we know the equation, that is K minimum is equal to root I minimum divided by A, right? So from here if we take square on both the side, then it will be K square minimum is equal to I minimum divided by A. And here we have this I minimum and here we have this area. So here we can replace this area and I minimum by K square. So if you will simplify this, then you will get PR is equal to sigma C into A divided by 1 plus sigma C divided by pi square E into bracket LE by K minimum square. And here this is the equation of Rankine's formula, or we can say it is the equation of Rankine's load. Fine. And here in this equation we can take this sigma C divided by pi square E as Rankine's constant, that is denoted by C. So if you will take this term as Rankine's constant, then this formula will become this. So finally we will have PR is equal to sigma C into A divided by 1 plus C into LE divided by K square. And here this value of K, that is radius of gyration, is K minimum. Fine. So if you want to remember this equation, then you can remember. And if you don't want to remember this equation, then you can also find value of PR from this equation. In this equation, you know the value of PE, that is this, and you also know the value of PC, that is this. So you can also find value of PR by finding these two values and then putting that values here. So I think that will be more easier. Fine. Now understand one thing, that for brittle material, compressive strength of material is higher than shear strength of material, and that is higher than tensile strength of material. And for ductile material, compressive strength is higher than tensile strength and it is higher than shear strength. Means for both the type of material, compressive strength is higher than tensile strength in the body. Fine. So in most of the case, we take our member in compressive load rather than tensile load. Means we will try to apply compressive load in the member rather than tensile load. Fine. So here there is one concept of core. So now we will discuss core. So what is core? It is the portion of area of cross-section area in which if load is applied, then there is no tensile stress produced in the member. So we will understand this core by one example. Let's say we have this column which is having circular cross-section as shown here and which is fixed at bottom surface. We apply one compressive load P at the eccentricity of E. Means here distance between this centroidal axis and line of action of this load is E. So here we know that what is going to be the value of stress in this column by this load P. If we want to find out effect of this load on this member, then we have to transfer this load P on the centroidal axis of this member. Let's say here this is the centroidal axis and here we apply load P and this distance is E. Now to transfer this P load on this axis at this point, we are going to apply two loads having equal magnitude and opposite direction at this point. So it is like this. And here value of the magnitude of both the load is P. And now we know that here these two loads will produce a couple in this member. And it will be one moment in the clockwise direction, right? And it will be having value M is equal to P into E, right? So now we can understand that on this body there will be one compressive load P and there will be one moment in clockwise direction having value P into E. Now we know that there will be stress in this body by this compressive load and by this moment. By this compressive load P, there will be stress in this direction like this and it will be uniform, and by this moment there will be stress in this member. So if I draw stress variation, then it will be something like this. On this side it will be upward in direction and on this side it will be in this direction. So actually on this side it is having compressive stress and also there is tensile stress, right? And if we want to find out core area, then we want that this material or this member should only have compressive load in the member. There should not be any tensile stress in the member. And finally, stress will be in this member will be total of this both the stresses. Fine. So we can find out that total stress that will be equal to P divided by A, that is stress by this load P, plus there will be stress by this bending moment applied on this body, and that will be My divided by I. On this surface there is tensile stress is applied. So we are going to find this stress on this surface. And here this load is compressive load. So we are going to take this load as negative and we will take this stress as positive because on this surface it is tensile in nature. Fine. Now what is going to be the value of Y? For this surface, Y is this distance. That is D divided by 2, right? And what will be the value of I? We know that for circular cross section, I is equal to pi by 64 into d raised to 4. And we also know that area is equal to pi by 4 d square. So now we have to put these values here. So we will get sigma is equal to minus P divided by pi by 4 d square plus M, that is equal to P into E, into Y, that is d by 2, divided by this I, which is equal to pi by 64 into d raised to 4. Now we want that there should be only compressive stress in the body. There should not be any tensile stress in this body. And for that we have to take sigma should be less than or equal to 0. Means here these terms should be less than or equal to 0. Fine. So if you will simplify this, then you will get E should be less than or equal to d by 8 for sigma less than or equal to 0. Means here if the value of this eccentricity is less than or equal to d by 8, then there will be only compressive stress in this member. For value of E less than or equal to d by 8, there will be no tensile stress in this member. So we have to apply this load P at the distance less than or equal to d by 8 to get only compressive stress in the member. Clear? Now here this load should be at anywhere on this member at the distance of E. Here we apply load at this point, and here this distance is E. We can also apply load at this point or this point or this point, or we can also apply it here. But here distance between this point and this point, that is E, should be less than or equal to d by 8, right? So now we can find out area on which we can apply this load P. And here that area will be equal to pi into E square, right? Generally the equation of finding out area of circular cross section is pi r square, but here r is equal to E. So this area is pi into E square, and that is equal to pi d square by 64, because here this E is having maximum value d by 8. So we can say that this is the area on which we can apply this P load, and there will be only compressive stress in the body. And here this area is called as core. Fine. And here that area is shown here. This is the area which is called as core. And if we apply this P load on this area, then we will get only compressive stress in the body. Fine. So I hope that you understand this concept. It is not very important as per the GATE point of view, but here I have given you only for your understanding. Fine. So from this chapter you have to remember few formulas, and by using them you will be able to answer any question from this chapter. And here this chapter is completed, and from next video we will start new chapter. Till then read the notes and try to understand the concept and remember the formulas. So we will meet in the next video. Till then stay motivated and happy practicing.